So here's something worth thinking about as you settle in tonight. Right now, above your head, roughly 250 miles up, there is a structure about the size of a football field, moving at 17,500 miles per hour. Inside it, somewhere between 3 and 7 people are living their lives. Someone up there might be eating dinner. Someone might be running on a treadmill strapped to it with bungee cords so they don't float away. Someone might be looking out a window at the curve of the earth, watching a sunrise, their 16th of the day, because at that speed, you circle the planet every 90 minutes. That structure is the International Space Station, and it is, by almost any measure, the most complex thing human beings have ever built. But it didn't start there. The story of how we learned to live in space, how we figured out the engineering, the life support, the psychology, the orbital mechanics, all of it. That story stretches back decades before the first module ever reached orbit. And it's a story full of surprises, false starts, impossible engineering problems, and some genuinely brilliant people who refused to accept that something couldn't be done. Let's start at the very beginning. Not with hardware, not with rockets, with an idea. The concept of a space station, a permanent place to live and work in orbit, is older than you might think. Way older than the space age itself. A Russian schoolteacher named Konstantin Tsiolkovsky was writing about this in the 1890s. The 1890s. Think about that for a second. The Wright brothers hadn't flown yet. Most people were still getting around on horses. And this man, teaching math and physics in a small town called Kaluga, was sketching out detailed ideas about how humans could live in space. He wrote about pressurized cabins, about airlocks, about growing food in orbit using sunlight. He even worked out the basic math of how a rocket would need to work to get there, the famous Tsiolkovsky rocket equation, which is still one of the foundational equations of spaceflight. And he described something that would become central to the whole idea of space stations: rotation to create artificial gravity. Now, Tsiolkovsky never built anything. He was a theorist, a dreamer, and honestly, a bit of an eccentric. He was nearly deaf from a childhood illness, and he spent most of his life in relative obscurity. But his writings planted seeds, and those seeds would germinate in some remarkable places. The next person who really pushed the idea forward was a man named Hermann Oberth, a Romanian-born German physicist who published a landmark book in 1923 called, roughly translated, The Rocket into Planetary Space. Oberth laid out the physics of orbital mechanics in rigorous detail and described a station in orbit that could serve as a platform for observing the Earth and as a jumping-off point for missions deeper into space. He was thinking about this not as science fiction, but as engineering. What would you actually need? What problems would you actually face? And one of his readers, a young man who would become perhaps the most famous rocket engineer in history, took those ideas and ran with them. That young man was Wernher von Braun. And here's where the story gets complicated. Because the history of space stations, like the history of rocketry in general, runs straight through the darkest chapter of the 20th century. Von Braun was brilliant, ambitious, and obsessed with spaceflight from childhood. He joined the German Rocket Society as a teenager, and by his mid-20s, he was the technical director of Nazi Germany's V2 rocket program at Peenemünde. The V2 was a terrifying weapon, the world's first long-range ballistic missile, used to bomb London and Antwerp in the final years of World War II. Thousands of people were killed by V2 strikes, and thousands more, slave laborers, many of them concentration camp prisoners, died building the rockets in the underground factories at Mittelwerk. This is not a footnote. This is part of the foundation. The same engineering knowledge that would eventually put stations in orbit was developed, in part, under conditions of horrific cruelty. After the war, von Braun surrendered to the Americans and was brought to the United States, along with more than 100 other German rocket scientists, under Operation Paperclip. And it was in America, in the early 1950s, that von Braun became a public evangelist for space exploration. He wrote articles for Collier's magazine, a hugely popular publication at the time, describing in vivid detail his vision for the future of spaceflight. And at the center of that vision was a space station. Von Braun's station design was gorgeous. It was a giant wheel, 76 meters in diameter, rotating slowly to produce artificial gravity for the crew inside. It would orbit at about 1,000 miles up, crewed by 80 people, and it would serve as an astronomical observatory, a microgravity research lab, and a staging point for missions to the Moon and Mars. The Collier's articles, illustrated beautifully by the artist Chesley Bonestell, captured the American imagination. Disney even hired von Braun to appear in a series of television specials about space. Millions of people saw these programs, and the rotating wheel station became the iconic image of what living in space would look like. Here's the thing, though. That wheel station, that beautiful, elegant, spinning design, was never built. And the reasons why tell you a lot about how real engineering works versus how we imagine it working. The problem wasn't that the physics was wrong. Rotation really can simulate gravity. If you spin a structure in space and you're standing on the inside of the outer rim, the centripetal acceleration pushes you outward and your feet press against the floor in a way that feels a lot like weight. The math checks out. The problem was everything else. Building a structure that large in orbit would require an enormous number of launches. You'd need to assemble it in space, which means you need spacewalking astronauts or sophisticated robotic systems, neither of which existed. The structure would need to be rigid enough to maintain its shape while spinning, which introduces serious structural engineering challenges. And the rotation itself creates complications, Coriolis effects that make moving around inside the station disorienting, differential forces between your head and your feet if the wheel isn't big enough, difficulties docking other spacecraft to a rotating structure. Every one of these problems is solvable in principle, but solving them all simultaneously with 1950s or even 1960s technology, while also figuring out how to keep people alive in space at all, it was just too much, too soon. So what actually happened was both less glamorous and, in its own way, more interesting. Instead of building the grand vision all at once, engineers on both sides of the Cold War started small, very small. They started by figuring out the most basic question of all. Can a human being survive in space for more than a few hours? This is worth pausing on, because we take it for granted now. But in the late 1950s, there were serious scientists who worried that prolonged weightlessness might be fatal. Nobody knew for sure what would happen to the human heart when it didn't have to pump blood against gravity. Nobody knew if you could swallow food in 0G. There was genuine concern that without gravity, food might not travel down your esophagus properly. Nobody knew what would happen to your bones, your muscles, your inner ear, your vision. The only way to find out was to send people up and see. The first space stations, then, weren't stations in the way von Braun imagined. They were more like cramped apartments bolted onto the top of rockets and hurled into orbit. And the first nation to actually do it was the Soviet Union. The Soviet space station program grew out of a military project. In the mid-1960s, a design bureau led by Vladimir Chelomey one of several rival Soviet spacecraft designers, was working on a military orbital station called Almaz. The idea was to put military cosmonauts in orbit to conduct reconnaissance, essentially a crewed spy satellite. Almaz was a serious program, with real hardware being built, but it was falling behind schedule. Meanwhile, another design bureau, the one led by the legendary Sergei Korolev, though Korolev himself had died in 1966, was developing civilian spacecraft and had the Soyuz capsule coming along nicely. What happened next was pure Soviet bureaucratic maneuvering. Korolev's bureau, now led by Vasily Mishin, proposed taking an Almaz hull, basically the pressurized cylinder that Chelomey's team had designed, and outfitting it with Soyuz-derived systems to create a civilian space station that could be launched quickly. The goal was to beat the Americans, who were known to be planning their own station. The result was Salyut 1, and it launched on April 19, 1971. Now, Salyut 1 was not a sophisticated machine by modern standards. It was essentially a single cylinder, about 20 meters long, and a little over 4 meters in diameter at its widest point. Inside, the total habitable volume was roughly 90 cubic meters. Imagine a space a bit smaller than a modest studio apartment, except everything is floating, including you. It had a telescope, some scientific instruments, an exercise bicycle, and a small garden experiment. Life support was relatively simple: chemical canisters to scrub carbon dioxide from the air, stored water and food, and systems to maintain temperature and humidity. There was no shower. The toilet was rudimentary at best, but it was a real place in space where people could live and work for days or weeks at a time, and that was revolutionary. The first crew sent to Salyut 1, the Soyuz 10 crew, actually failed to enter the station. They docked, but the docking mechanism malfunctioned, and they couldn't open the hatch. They had to come home without ever getting inside. Think about the frustration of that. You've trained for months. You've ridden a rocket into orbit. You can see the station right there through your window, and you just can't get in. The hatch won't open. The engineering of the docking system, the latches, the seals, the alignment mechanisms, wasn't quite right. The second crew, though, Georgy Dobrovolsky, Vladislav Volkov, and Viktor Patsayev aboard Soyuz 11. They made it inside. They entered Salyut 1 on June 7, 1971, and they lived there for 23 days. 23 days in space, in a real space station. They conducted experiments. They observed the Earth. They exercised. They dealt with a small fire in the station at one point, and they proved that human beings could live and work in orbit for extended periods. It was a triumph. And then, on June 30th, 1971, they climbed back into their Soyuz capsule and undocked for the trip home. And during re-entry, a pressure equalization valve in the Soyuz descent module opened prematurely. At an altitude where the atmosphere is essentially vacuum, the cabin depressurized. The 3 cosmonauts were not wearing pressure suits. The Soyuz 11 cabin was too small for 3 suited crew members, so the decision had been made to fly without suits. All 3 men died of asphyxiation before the capsule reached the ground. The recovery team found them still strapped in their seats, motionless. There was no external damage to the capsule. The landing had been perfect, but the crew was gone. This is one of those moments in the history of spaceflight that demands we stop and sit with it. 3 men who had just accomplished something extraordinary, who had lived in a space station, who had proven it could be done, killed by a valve. A single valve, about the size of a coin, that opened when it shouldn't have. The engineering investigation afterward found that the valve, designed to equalize cabin pressure with the outside atmosphere during the final phase of descent, had been jarred open by the pyrotechnic bolts that separated the orbital module from the descent module. The shock of the explosive bolts traveled through the structure and triggered the valve early, at an altitude of over 160 kilometers, where opening that valve meant instant decompression. The Soviet space program was shaken to its core, and the changes that followed were profound. From that point on, Soyuz crews would always wear pressure suits during launch and re-entry. The Soyuz capsule was redesigned to accommodate suited crew, which meant reducing the crew from 3 to 2 for many years, until a redesigned version could fit 3 suited cosmonauts. Every future space station program, Soviet and American alike, would carry the lesson of Soyuz 11 in its DNA. Space is unforgiving, and the margin between life and death can be a single valve, a single seal, a single decision about what safety equipment to carry. But the program continued, because the Soviets understood something important, something that would shape the next 2 decades of space station development. They understood that the way to learn how to live in space was to keep doing it, to keep building stations, to keep sending crews, and to keep solving problems one at a time. And the station they built next, and the ones after that, would begin to answer questions that nobody had ever seriously asked before. Not just, can humans survive in space? Soyuz 11 had tragically proven that yes, they could live and work up there, but the journey home could kill them. But deeper questions. How long can a human body actually tolerate weightlessness? What happens to your muscles after a month? Your bones? Your heart? What does it take to keep a space station running, not for 3 weeks, but for 3 months, or 6, or a year? And what kind of engineering do you need to support that? So let's talk about what came next. Salyut 2 launched in April of 1973, just about 2 years after Salyut 1. And here's where the tangled history of the Soviet program gets interesting, because Salyut 2 wasn't actually a civilian station at all. It was one of Chelomey's military Almaz stations, flying under the Salyut name to disguise its true purpose. The Soviets were clever about this. They used the same public name for both the civilian and military stations, so Western observers couldn't easily tell which was which. Salyut 2 was designed for military reconnaissance, essentially a crude spy platform in orbit. But it never got the chance to prove itself. Shortly after reaching orbit, the station suffered a catastrophic failure. The propulsion section depressurized, attitude control was lost, and the station tumbled. No crew ever visited it. It broke apart and re-entered the atmosphere about a month later. Then came Cosmos 557, launched just 11 days after Salyut 2, which was actually a civilian DOS station, the same lineage as the original Salyut 1. It also failed almost immediately, burning through its attitude control fuel due to a systems malfunction before any crew could reach it. So now, you've got 2 station failures back-to-back in the spring of 1973. Think about what that feels like for the engineers. They've already lost 3 cosmonauts. They've now lost 2 stations in a row, and the Americans, meanwhile, are about to launch Skylab. Let's pause on Skylab for a moment, because it's a fascinating contrast in philosophy. While the Soviets were building small, relatively simple stations and planning to iterate, launch one, learn from it, launch another, the Americans took a completely different approach. Skylab was big. Really big. It was built from the upper stage of a Saturn V rocket, the same rocket that sent astronauts to the moon. The orbital workshop module was about 6.7 meters in diameter and roughly 13 meters long. For context, that's about the size of a modest house. The total habitable volume was around 320 cubic meters, which was enormous for the time, far larger than anything the Soviets had flown. A single astronaut could float into the workshop and do somersaults without touching the walls. There was a wardroom with a table where the crew could sit, float, and eat together, looking out a window at the Earth below. There was a shower of sorts. There were separate sleeping compartments. It felt, for the first time, like a place where people could actually live, not just survive. But here's the thing about Skylab. It almost didn't work at all. During launch on May 14, 1973, the micrometeoroid shield, which also served as a thermal shield, was torn off by aerodynamic forces. One of the two main solar array wings was ripped away entirely, and the other was jammed shut by debris. So Skylab reached orbit crippled, overheating because it had lost its sun shield, and critically short on electrical power because it had lost most of its solar panels. The first crew, Pete Conrad, Joe Kerwin, and Paul Weitz, launched 11 days later on a rescue mission as much as a science mission. They carried a parasol-like sunshade that they deployed through a scientific airlock, essentially pushing it out and letting it unfurl over the damaged area like an umbrella. Then, during a daring spacewalk, Conrad and Kerwin managed to free the jammed solar panel using a tool that was basically a long pole with cable cutters on the end. They literally stood on the outside of the station and yanked the panel free. When it finally swung open, the station came alive with power. And this is worth sitting with for a moment, because it illustrates something fundamental about space stations that would prove true over and over again for the next 50 years. They break. They always break. Something always goes wrong. Something always fails in a way nobody predicted. And the question is never whether you'll face a crisis, but whether you've designed enough flexibility into the system and trained your crew well enough to improvise a solution. Skylab's engineers on the ground designed that parasol sunshade in about 10 days. They tested it in a swimming pool, figured out how to pack it into the airlock, and talked the crew through deploying it. That combination of ground-based engineering and crew resourcefulness became the template for every space station emergency response that followed. Skylab hosted 3 crews over about 9 months in 1973 and 1974. The missions got progressively longer, 28 days, then 59 days, then 84 days. And the medical data they gathered was invaluable. They confirmed what Soviet doctors had begun to suspect. Weightlessness does real things to the human body. Muscles atrophy. Bones lose calcium. The heart, which on Earth has to pump blood upward against gravity, starts to get a little lazy when there's no up or down. Body fluids redistribute. On Earth, gravity pulls fluid into your legs, but in space, it migrates toward your head, which is why astronauts often look puffy-faced in photographs. Their legs get thinner, their faces get rounder. It's sometimes called chicken leg syndrome, which is a slightly undignified name for a genuine medical concern. But here's what was encouraging. The astronauts recovered after returning to Earth. Their bones and muscles bounced back mostly, and the Skylab crews demonstrated that exercise helped. The third crew, who had the most rigorous exercise regimen, came back in better shape than the first 2. This was a crucial insight. It meant that with the right countermeasures, long-duration spaceflight was medically feasible. You just had to work at it. And that finding shaped every space station exercise program that followed, right up to the 2-hour daily workout that astronauts on the International Space Station do today. Now, Skylab was a triumph in many ways, but it was also a dead end. There was no plan to resupply it, no way to send up new modules or expand it. It was a single piece of hardware, launched all at once, and when the last crew left in February 1974, that was it. NASA had vague plans to use the space shuttle to reboost Skylab's orbit and maybe revisit it, but the shuttle took longer to develop than expected, and Skylab's orbit decayed faster than predicted. In July 1979, Skylab re-entered the atmosphere, scattering debris across the Indian Ocean and parts of Western Australia. The Shire of Esperance, a local government area in Western Australia, famously sent NASA a $400 fine for littering. It went unpaid for decades until a radio DJ finally settled it in 2009. But while the Americans were done with space stations for a while, they wouldn't have another one until the shuttle era. The Soviets were just getting started. And this is where the Soviet approach really begins to pay off. Remember, their philosophy was iterative. Build a station, fly it, learn from it, build a better one. And that's exactly what they did through the mid and late 1970s. Salyut 3, launched in 1974, was another military Almaz station in disguise. It actually worked this time. A crew visited, conducted reconnaissance activities, and the station reportedly even test-fired a modified aircraft cannon, which, if true, makes it the only space station to have ever fired a weapon. Salyut 4, launched later that year, was a civilian station that hosted 2 crews and operated successfully for about 2 years. Salyut 5, in 1976, was the last of the military Almaz stations to fly. Each one was a little better, a little more refined, a little more capable. But the real leap came with Salyut 6, launched in September 1977. And this is the station where the Soviets genuinely figured out how to live in space long-term. So let's slow down here, because the engineering innovations on Salyut 6 were game-changing. The single biggest difference was this. Salyut 6 had 2 docking ports. Every previous Salyut had only 1. That might sound like a small thing, but think about what it means. With 1 docking port, a crew arrives in their Soyuz, docks, and that Soyuz sits there the whole time, blocking the only port. Nobody else can visit. No supplies can be delivered. The crew is limited to whatever they brought with them, and whatever was already on the station when it launched. With 2 ports, 1 on each end of the station, everything changes. A crew can dock at one end, and a supply ship can dock at the other. Or a second crew can come up for a short visit, while the first crew stays. This was the key that unlocked long-duration spaceflight, because it meant the station could be resupplied. And the Soviets developed a spacecraft specifically for this purpose, the Progress cargo vehicle. Progress was essentially an uncrewed version of the Soyuz, modified to carry fuel, food, water, air, equipment, and even personal mail for the cosmonauts. It would dock automatically at the second port. The crew would unload it, then fill it with trash and waste, and it would undock, deorbit, and burn up in the atmosphere. It was, in effect, the world's most expensive garbage truck. But it was also the innovation that made permanent human presence in space possible. You can't live somewhere indefinitely if you can't get deliveries. Progress solved that problem, and versions of the Progress spacecraft are still flying to the International Space Station today, nearly 50 years later. The basic design was that good. Salyut 6 hosted 16 crews over nearly 5 years of operation. The longest single stay was 185 days, just over 6 months, set by Leonid Popov and Valery Ryumin in 1980. 6 months. Think about what that means in terms of life support engineering. The station's systems had to keep recycling air, managing carbon dioxide levels, controlling humidity, regulating temperature, and handling waste for half a year without a major failure. The environmental control system used lithium hydroxide canisters to scrub carbon dioxide from the air, electrolysis units to generate oxygen from water, and condensers to pull moisture out of the atmosphere. None of these systems were perfect. The cosmonauts often complained about humidity, odors, and the general stuffiness of the cabin, but they worked well enough to keep people alive and functional for months at a stretch. And here's something you might not think about: thermal control. In space, managing heat is one of the trickiest engineering problems you face. There's no air to carry heat away through convection, so the only way to shed excess heat is through radiation. The station's electronics, the crew's bodies, sunlight hitting the hull, all of these generate heat that has to go somewhere. Salyut 6 used a system of fluid loops that circulated a coolant through the station, picking up heat from the interior and carrying it to external radiators, where it could be radiated away into the cold of space. On the shadow side of the orbit, when the station was in Earth's shadow, the exterior could plunge to extremely low temperatures, and the same system had to prevent things from getting too cold. So the thermal control system was constantly balancing, dumping heat when there was too much, conserving it when there wasn't enough. It's like the thermostat in your house, except your house doesn't swing between direct sunlight and deep shadow every 45 minutes. Salyut 7 followed in 1982, and it pushed the envelope even further. Longer crews, more complex science, and the first modular expansion of a space station. A small add-on module called Cosmos 1686 was docked to the station late in its life. But Salyut 7 is perhaps best remembered for one of the most dramatic rescue missions in the history of spaceflight. In February 1985, after the station had been unoccupied for several months, ground controllers lost contact. The station went silent. Telemetry dried up. Something had gone badly wrong, and nobody on the ground knew exactly what. The station was tumbling, uncontrolled, and freezing cold in the darkness of space, and the Soviets decided to send 2 cosmonauts to fix it. Vladimir Janibekov and Viktor Savinik launched aboard Soyuz T-13 in June 1985 on what might be the most harrowing docking approach ever attempted, because they were approaching a dead station. No lights, no radar transponder, no communication, no cooperation from the target at all. Janibekov had to fly the Soyuz manually, using visual cues, matching the tumble of the station and easing the Soyuz in close enough to dock by hand, judging distance and rotation with nothing but his eyes and his experience. Think about what that actually requires. You're in a small capsule, approaching a 7-ton station that's slowly rolling in the dark, and you have to match its rotation, line up your docking probe with the receiving port, and make contact gently enough that you don't damage either vehicle. All while knowing that if you misjudge the approach, there's no second chance, because your fuel is limited and the station isn't going to help you. Janibekov was one of the most experienced pilots in the Soviet cosmonaut corps, and by all accounts, he flew it beautifully. He brought the Soyuz in slowly, matched the station's drift, and achieved a soft dock on the first attempt. It remains one of the finest pieces of manual piloting in the history of human spaceflight. But docking was just the beginning. When Janibekov and Savinik opened the hatch and floated into Salyut 7, what they found was eerie. The station was completely dead. No lights, no fans, no hum of electronics, just silence and freezing cold. Their breath formed clouds of vapor in the air. The temperature inside had dropped well below 0 Celsius. Frost covered the walls, the instruments, the windows. Water from the humidity in the atmosphere had condensed and frozen on every surface. It was, in the most literal sense, a derelict, a ghost ship in orbit. And here's the thing that made the situation genuinely dangerous. They couldn't just flip a switch and bring the station back. The electrical system was dead because the batteries had drained completely. The batteries had drained because the solar panels had stopped tracking the sun. And the solar panels had stopped tracking the sun because the attitude control system had failed, which meant the station was tumbling randomly and the panels were only occasionally catching sunlight, not enough to keep up with the station's power draw. So everything cascaded. One failure, the attitude control, led to another, loss of solar tracking, which led to another, battery drain, which led to total system death. It's a perfect example of how interconnected space station systems really are. Nothing exists in isolation up there. So Janibekov and Savinik had to work the problem backwards. First, they needed to get the solar panels pointed at the sun. They used the Soyuz's own thrusters to manually orient the whole combined stack, the Soyuz plus the dead Salyut, so that the station's solar panels faced sunlight. Then they waited. Slowly, painfully slowly, the panels began to trickle charge into the frozen batteries. But frozen batteries don't charge well. Some of them had cracked from the cold, so the cosmonauts had to figure out which battery packs were still functional, bypass the damaged ones, and coax enough charge into the survivors to begin powering up the most critical systems. They worked in the cold for days, wearing fur-lined caps and extra layers, their fingers numb, their breath still fogging. Gradually, they brought heaters online, then fans, then the environmental control systems. The frost on the walls began to melt, which created a new problem. Globules of water floating everywhere in microgravity, getting into electronics, shorting things out. They spent hours mopping up water with towels, wringing them out into a collector. It was unglamorous, exhausting, freezing work, and it saved a space station. Within a couple of weeks, Salyut 7 was alive again. The environmental systems were running, the power was stable, and the station was back under control. Janibekov and Savinik had pulled off something that, honestly, reads more like science fiction than engineering history. And the lessons from that rescue, about system redundancy, about the cascading nature of failures, about the importance of being able to manually override automated systems, those lessons fed directly into the design of what came next. Because what came next was Mir. Mir is where the story of space stations really shifts gears. Everything before Mir, the Salyuts, Skylab, even the military Almaz stations, those were essentially single modules. One pressurized cylinder, launched in one piece, with maybe a small add-on docked later in the case of Salyut 7. Mir was different. Mir was designed from the beginning to be modular. A core module with multiple docking ports where additional specialized modules could be attached over time, growing the station piece by piece. This was the fundamental architectural concept that would eventually define the International Space Station, and the Soviets pioneered it with Mir. The core module launched on February 20th, 1986, aboard a Proton rocket. And if you think about it, the timing is remarkable. This was just a month after the Space Shuttle Challenger disaster, which grounded the American shuttle fleet for nearly 3 years. While NASA was reeling from that tragedy, the Soviet space program was launching the most ambitious space station ever attempted. The core module of Mir was derived from the Salyut design. It was about 13 meters long and 4 meters in diameter, roughly the size of a large bus. But it had a critical new feature. At the forward end, instead of a single docking port, there was a spherical node with 6 docking ports. one axial port at the front, one at the back connected to the main body of the station, and 4 radial ports arranged around the sides of the sphere. This meant that up to 5 additional modules could be attached to the core, each one brought up separately and docked to one of those ports. Now, here's what's really clever about how they actually assembled it. The radial ports on that node were relatively small, and the modules being attached were large and heavy. You can't just fly a 20-ton module sideways into a radial port with precision. The approach angles are all wrong, and the docking systems of the era weren't designed for that kind of lateral maneuvering. So instead, each new module would first dock at the axial port, the one straight ahead at the front of the station, using a standard approach. Then, a robotic arm on the outside of the node, called the LIAPA arm, would grab the module and physically swing it from the axial port over to its assigned radial port. It's a beautifully pragmatic solution. Rather than inventing a whole new docking system for lateral approaches, they just used the existing one and added a mechanical arm to reposition the module after arrival. The first expansion module, Cavant 1, arrived in 1987. It was an astrophysics module carrying X-ray telescopes and other instruments, and it actually docked at the rear axial port rather than the front, which was a slightly different arrangement. Cavant 1 had a troubled docking. It wouldn't seat properly at first, and cosmonauts had to do a spacewalk to investigate. They found a trash bag, literally a bag of garbage that had been left in the docking cone during a previous Progress resupply mission, was preventing a clean seal. They removed it, and Cavant 1 locked into place. A trash bag nearly derailed the expansion of humanity's most advanced space station. That's spaceflight for you. Cavant 2 followed in 1989, adding a large airlock for spacewalks, additional life support equipment, and scientific instruments. Then Crystal in 1990, which carried materials, science experiments, and a docking port designed to eventually receive the American Space Shuttle. Spectre came in 1995, loaded with scientific instruments and additional solar arrays, and Perroda arrived in 1996, focused on Earth observation. Each module added capability, power, and volume to the station, and by the time Mir was fully assembled, it was a genuinely complex orbital facility, about the size of 6 school buses connected together, with a pressurized volume you could actually move around in. But here's what made Mir truly revolutionary beyond its architecture. It was continuously inhabited for almost 10 years. From September 1989 to August 1999, there was always someone living aboard Mir. 10 years of unbroken human presence in orbit. That had never been done before, and the sheer duration of the program generated an enormous body of knowledge about what happens to people and machines during long-duration spaceflight. The human body stuff is fascinating and a little unsettling. We talked earlier about how Skylab showed that exercise could slow down the bone loss and muscle atrophy caused by weightlessness. Mir confirmed that and pushed the understanding much further. Cosmonauts on Mir exercised for 2 hours every single day, running on a treadmill, pedaling a stationary bicycle, pulling on resistance bands, and they still lost bone density. The rate was roughly 1 to 2% per month in the load-bearing bones, the hips and spine and legs. Think about that. Even with aggressive daily exercise, you're losing bone at a rate that, over a year-long mission, could leave you with the skeletal density of a 70-year-old. And the recovery after returning to Earth took months, sometimes longer than the mission itself. The cardiovascular system presented its own challenges. In microgravity, without the constant pull of gravity, your body redistributes its fluids. blood and water that normally pool in your legs get pushed up towards your head and chest. Your heart, which on Earth has to work hard to pump blood up to your brain against gravity, suddenly finds its job easier, so it starts to decondition, to lose muscle mass, just like any muscle that isn't being challenged. When cosmonauts returned to Earth after months on Mir, some of them could barely stand. Their hearts had weakened, their blood pressure regulation was off, and their bodies had forgotten how to handle gravity. The Russian medical teams developed increasingly sophisticated countermeasure programs, specific exercise regimens, fluid loading protocols before re-entry, even lower body negative pressure devices that simulated the gravitational pull on the legs by creating a partial vacuum around the lower body. All of this was worked out on Mir, through trial and error, over years. And then there were the psychological challenges, which honestly might be the hardest engineering problem of all. Except you're engineering a social environment instead of a machine. Mir crews were small, typically 2 or 3 people, confined to a space the size of a modest apartment for months at a time. They were far from home, in constant danger, with communication delays and limited contact with family. Interpersonal friction was real and sometimes severe. There were documented cases of crew members barely speaking to each other for weeks. Ground control had to learn how to manage crew psychology as carefully as they managed the station's orbit, scheduling surprise care packages from family, arranging special meals, being sensitive to workload and rest time. The station itself aged in ways that taught engineers enormous lessons about long-duration hardware. Mir was designed for a 5-year operational life. It lasted 15. And by the end, it was showing its age in ways that ranged from annoying to terrifying. The environmental control system, which had been running continuously for over a decade, developed persistent problems. The electron-oxygen generation units, which split water into hydrogen and oxygen through electrolysis, broke down repeatedly. When they failed, the crew had to fall back on backup oxygen sources, solid fuel oxygen generators, essentially chemical canisters that produced oxygen through a controlled chemical reaction when ignited. In February 1997, one of these canisters malfunctioned and caught fire, producing a blowtorch-like flame that burned for about 14 minutes inside the station. 14 minutes of open flame in a sealed, oxygen-rich environment in orbit. The crew fought it with fire extinguishers while smoke filled the station, partially blocking the path to one of the 2 Soyuz escape capsules. It was, by every account, absolutely terrifying. They got it out. Nobody was killed. But it was a stark reminder that fire in space is one of the most dangerous scenarios imaginable. Because you can't open a window, you can't evacuate to the yard, and the air you're breathing is the same air feeding the flames. And that wasn't even Mir's worst day. Just a few months later, in June 1997, during a test of a new manual docking system for the Progress resupply vehicle, the cargo ship came in too fast and struck the Spectre module. The collision punctured the hull. Air began rushing out. The crew could hear the hiss, feel their ears pop as the pressure dropped. They had to scramble to disconnect the cables running through the hatchway into Spectre and seal the hatch before the entire station depressurized. They managed it, barely, but Spectre was permanently sealed off, and with it went several of the station's solar arrays, cutting the power supply dramatically. The station limped along for months afterward with reduced capability. These incidents, the fire, the collision, the constant equipment failures, they painted a picture of a station that was being pushed well beyond its design life. And some people looked at Mir's troubles and saw failure. But engineers looked at Mir's troubles and saw something invaluable. Data. Real Hard-won data about what breaks, how it breaks, when it breaks, and what you can do about it when you're 250 miles above the Earth with no hardware store in sight. Every failure on Mir became a lesson that was folded into the design of the International Space Station. The fire led to better material selection, better fire suppression systems, and stricter protocols about stowage and flammable materials. The collision led to improved docking procedures and better hull monitoring. The life support breakdowns led to more redundant systems with better diagnostic capabilities. And here's the other thing: Mir gave the world something that might matter just as much as the engineering data. It proved that international cooperation in orbit was possible. Starting in 1995, American astronauts began flying to Mir as part of the Shuttle Mir program. NASA astronauts lived aboard a Russian space station, launched on Russian rockets, ate Russian food, spoke Russian with their crewmates. It was awkward sometimes. There were cultural clashes, communication problems, and moments of genuine tension. But it worked, and it built the trust, the procedures, and the institutional relationships that made the International Space Station possible. Because the ISS, this extraordinary thing that's been orbiting over our heads since 1998, the ISS is fundamentally a partnership, and that partnership was rehearsed on Mir. The story of how the ISS came to be is itself a fascinating tale of politics and engineering colliding, because the station that eventually got built looks nothing like what anyone originally planned. NASA had been trying to build a space station since the shuttle became operational in the early 1980s. President Reagan announced Space Station Freedom in 1984, envisioning a large American station with contributions from Europe, Japan, and Canada. But Freedom was plagued by cost overruns and redesigns. It went through at least 4 major redesigns over nearly a decade, each one smaller and less capable than the last, as Congress kept cutting the budget. By the early 1990s, the program was in serious trouble, and then the Cold War ended. The Soviet Union dissolved in 1991, and suddenly the geopolitical landscape that had shaped spaceflight for 3 decades was completely different. Russia inherited the Soviet space program, the rockets, the stations, the expertise, the cosmonauts. But the Russian economy was in freefall. The space program that had built Mir, that had kept crews in orbit for over a year at a stretch, was struggling to keep the lights on. Engineers and scientists who had designed some of the most sophisticated spacecraft ever built were barely getting paid. There was a real fear in Washington and in Moscow that Russian rocket scientists and aerospace engineers, desperate for work, might start selling their expertise to countries you really didn't want having advanced missile technology. And at the same time, NASA's Freedom program was on life support. In 1993, the House of Representatives came within a single vote, literally one vote, 215 to 216, of canceling the entire thing. One vote away from America having no space station program at all. So you had this remarkable convergence. Russia had the expertise and the hardware, but not the money. America had the money and the political will, but a station design that kept getting redesigned into oblivion. And there was this strategic imperative to keep Russian aerospace engineers employed on peaceful projects rather than letting that talent scatter to the highest bidder. The Clinton administration, working with NASA Administrator Dan Golden, saw the opportunity. In 1993, the United States and Russia agreed to merge their space station programs. Freedom was dead. The Russian Mir 2 station, which had been planned as Mir's successor, was also effectively dead as a standalone project. But from the pieces of both, something new would emerge. They called it the International Space Station, and the partnership eventually grew to include 15 countries: the United States, Russia, Japan, Canada, and 11 member states of the European Space Agency. Think about what that means from an engineering standpoint. You're designing a structure that has to be built by different countries in different factories using different engineering standards and measurement systems, launched on different rockets, and it all has to fit together perfectly in orbit 300 kilometers above the Earth, where you can't exactly pull out a file and shave down a part that doesn't quite fit. The engineering challenge is immense, but honestly, the political and organizational challenge might have been even harder. Here's how they divided it up. Russia would provide the first two major elements, the propulsion and the initial living quarters. They'd also provide the Soyuz crew vehicles and Progress cargo ships, drawing directly on decades of experience with Salyut and Mir. The United States would provide the massive truss structure, the solar arrays, most of the laboratory space, and the life support systems for the American segment. Japan would build a beautiful laboratory module called Kibo. The word means hope, which would become the largest single pressurized module on the station. The European Space Agency would contribute the Columbus Laboratory, and Canada would provide something absolutely essential, the robotic arm system, Canadarm2, which would be used to assemble the station itself and handle cargo for decades to come. Now, the actual construction, and this is where it gets really interesting from an engineering perspective. The actual construction of the ISS is one of the most complex assembly projects in human history. Remember, you can't build a space station on the ground and launch it in one piece. It's far too large. The ISS, when completed, would have a pressurized volume roughly equivalent to a Boeing 747 and would stretch longer than a football field from the tips of its solar arrays. You have to launch it in pieces and assemble it in orbit, and each piece has to survive the violence of launch, then be maneuvered into position and connected to the growing structure with perfect precision. The first piece went up on November 20th, 1998. It was called Zarya, a Russian-built module, though actually funded by the United States, which is a nice little detail that captures the complicated nature of this partnership. Zarya means sunrise in Russian, and it was a functional cargo block, a descendant of the same TKS spacecraft design that Vladimir Chelome's bureau had developed back in the 1970s for the Almaz military stations. So there's this direct lineage, engineering DNA, if you will, running from the secret Soviet military space stations of the Cold War all the way to the first piece of the International Space Station. Zarya provided propulsion, power, and storage for the early station. It was launched unmanned on a Russian Proton rocket from Baikonur Cosmodrome in Kazakhstan, and it worked perfectly. 2 weeks later, the Space Shuttle Endeavour launched carrying the second element, Unity, also called Node 1, an American-built connecting module. Unity was a relatively simple cylinder with 6 berthing ports, 1 on each end and 4 around its circumference, designed to serve as a connecting passageway between modules. The shuttle crew used the robotic arm to grab Unity out of the payload bay and attach it to Zarya. And here's a detail that captures the precision required. The connection between these two modules used a system called the Common Berthing Mechanism, which NASA had developed specifically for the ISS. 2 modules would be brought close together, aligned to within incredibly tight tolerances, and then a series of 16 motorized bolts would draw them together, compressing seals to create an airtight connection. When those bolts finished tightening, astronauts could open the hatches and float from one module into the other. 2 pieces, built on different continents by different space agencies, connected in orbit, and the air didn't leak out. That's remarkable when you think about it. But here's the thing. After Unity was attached to Zarya, the station just sat there, unmanned, for almost 2 years. The next critical element, the Russian service module called Zvezda, was delayed repeatedly. Zvezda was essential because it would provide the station's primary life support, living quarters, and orbital control systems. Without Zvezda, nobody could live aboard the ISS. And Zvezda was late because Russia was struggling financially. The module was derived from the core module of the Mir-2 station that had been planned before the partnership, and it was being built at the Khrunichev factory in Moscow, but funding kept getting interrupted. NASA grew increasingly anxious. There were serious discussions about what to do if Zvezda never showed up. Backup plans involving interim control modules that the U.S. would build. It was a tense period that tested the partnership early, but Zvezda did arrive. It launched on July 12, 2000, on a Proton rocket and docked automatically with the Zarya Unity stack using the same kind of probe and drogue docking system the Russians had been perfecting since the Soyuz program in the 1960s. And once Zvezda was in place, the station was ready for people. On October 31st, 2000, Halloween, a Soyuz rocket launched from Baikonur carrying the first permanent crew. Expedition 1, commanded by American astronaut Bill Shepard, with Russian cosmonauts Yuri Gitsenko and Sergei Krikalev. They arrived on November 2nd and opened the hatches to a station that was cold, dark in places, and smelled of new plastic and metal. They turned on the lights, activated the life support, and began the permanent human habitation of the International Space Station, a continuous human presence in space that has not been interrupted since. As of now, there have been people living aboard the ISS every single day for over 24 years. Let that sink in for a moment. For nearly a quarter century, humanity has maintained a continuous presence in space. Now, what those early crews were living in was pretty Spartan compared to the finished station. Just 3 modules, Zarya, Unity, and Zvezda, with a combined pressurized volume smaller than a modest apartment. But the assembly was just getting started. And this is where the engineering becomes almost choreographic in its complexity. Over the next decade, more than 30 missions, a mix of space shuttle flights and Russian rocket launches, would deliver and install the remaining components. The assembly sequence had been planned with extraordinary care because each new piece had to maintain the station's overall balance, power, and thermal control. You couldn't just attach modules in any order you wanted. Each addition changed the station's center of mass, its thermal profile, its power budget, and its aerodynamic drag. The whole sequence was like a 3-dimensional puzzle being assembled by people in bulky spacesuits, working in vacuum, with the Earth spinning below them at 17,000 miles per hour. The backbone of the station is the integrated truss structure, a series of connected segments that stretch out perpendicular to the pressurized modules like the crossbar of a giant letter T. This truss is over 100 meters long, and it serves 2 critical purposes. First, it holds the solar arrays, those enormous golden wings you see in photographs of the ISS. There are 8 main solar array wings, and together they generate somewhere around 240 kilowatts of electrical power, which is roughly enough to power about 40 average American homes. The arrays track the sun, rotating on joints called solar alpha rotary joints, massive bearings about 3 meters in diameter that slowly turn the arrays to keep them pointed at the sun as the station orbits. And second, the truss carries the thermal control radiators, large white panels that radiate waste heat into space. Because here's something people don't always think about. In space, getting rid of heat is actually a bigger engineering challenge than staying warm. The station's electronics, life support systems, and even the crew themselves generate heat constantly, and in the vacuum of space, there's no air to carry that heat away through convection. The only way to reject heat is through radiation, emitting infrared energy into the cold of space. So the station uses a system of ammonia coolant loops that collect heat from inside the modules, carry it through pipes in the truss, and dump it through those radiators. If the cooling system fails, the station heats up fast and equipment starts shutting down. It's one of those systems that works so reliably, you forget it's there, but it's absolutely critical. And speaking of critical systems that work quietly in the background, let's talk about how you actually keep people alive inside this thing. Because life support on the ISS is one of the most elegant and underappreciated pieces of engineering on the entire station. The fundamental problem is straightforward to state and fiendishly difficult to solve. You have 6 or 7 human beings sealed inside a metal container in the vacuum of space, and they need to breathe, drink, water, stay at a comfortable temperature, and not be poisoned by their own metabolic waste products. Every breath they take consumes oxygen and produces carbon dioxide. Every drop of water they drink eventually becomes urine or sweat or moisture in their exhaled breath. Every hour, their bodies release trace amounts of volatile organic compounds, things like formaldehyde and ammonia and acetone, just from normal metabolism. And if you don't deal with all of that continuously, the atmosphere inside the station becomes toxic surprisingly quickly. Some estimates suggest that without active carbon dioxide removal, CO2 levels inside a sealed module could reach dangerous concentrations in less than a day. So let's walk through how the station handles each of these challenges, because the engineering is genuinely beautiful once you see how it all fits together. Start with oxygen. You need about 0.84 kilograms of oxygen per person per day, roughly. For a crew of 6, that's a little over 5 kilograms a day. Now, you could just haul oxygen up from Earth in pressurized tanks, and in the early days of the ISS, that's partly what they did. The Russian Electron system installed in the Zvezda module was the first onboard oxygen generator, and it works on a principle that's elegant in its simplicity. Electrolysis. You take water, pass an electric current through it, and the water molecule splits into its component parts, hydrogen and oxygen. The oxygen goes into the cabin atmosphere, and the hydrogen, well, in the early systems, the hydrogen was just vented overboard into space. Wasteful, but simple and reliable. The Electron unit has been a workhorse, but it's also been temperamental. It's had numerous shutdowns over the years, sometimes from air bubbles getting into the water supply, sometimes from contamination. When it goes down, the crew switches to backup systems, solid fuel oxygen generators, sometimes called oxygen candles, which are canisters of lithium perchlorate that, when ignited, undergo a chemical reaction that releases oxygen. These are the same type of device that caused the fire on Mir in 1997, so you can imagine the crew treats them with considerable respect. They work, they're reliable as a backup, but nobody loves having to use them. On the American side of the station, there's a more advanced system called the Oxygen Generation System, or OGS, which is also based on electrolysis but is designed to be more robust and more integrated with the station's overall life support architecture. It's housed in a rack in the Destiny Laboratory module and can produce enough oxygen for a full crew. The water it uses comes from, and here's where the system starts to get really clever, the station's water recycling system. but we'll get to that in a moment. First, let's talk about carbon dioxide, because removing CO2 is arguably even more critical than generating oxygen. Your body produces about a kilogram of carbon dioxide per day, and CO2 is insidious. At low concentrations, maybe around 1%, you start getting headaches, difficulty concentrating, a kind of foggy feeling. At 2 to 3%, the headaches become severe, you get dizzy, your judgment deteriorates. Above 5%, you're in serious danger, confusion, loss of consciousness, eventually death. And the thing about CO2 is it doesn't trigger that gasping, suffocating feeling the way a lack of oxygen does. You can be slowly poisoned by rising CO2 levels and not really notice until your cognitive function is already degraded. So the station monitors CO2 levels constantly and scrubs it from the air actively. The original CO2 removal system on the Russian segment uses a chemical absorbent approach, canisters of lithium hydroxide that react with carbon dioxide to form lithium carbonate, trapping the CO2 in solid form. These canisters are expendable. Once they're used up, they become waste. It works, but it means you have to keep launching fresh canisters. The American segment took a different approach with a system called the Carbon Dioxide Removal Assembly, or CDRA. This is a regenerable system, meaning it can be used over and over. It uses beds of a material called zeolite, which is a microporous mineral. Think of it like a molecular sponge with tiny, tiny pores that are just the right size to trap CO2 molecules. Air from the cabin gets pushed through these zeolite beds, and the CO2 sticks to the material. Then, when the bed is saturated, the system heats it up and exposes it to the vacuum of space, which causes the CO2 to release, a process called desorption. The CO2 gets vented overboard, and the zeolite bed is ready to be used again. The system has two beds that alternate. One is actively scrubbing CO2 from the cabin air, while the other is being regenerated. It's a continuous cycle. Now here's where it gets really interesting. That vented CO2 represents a lost resource. Every molecule of CO2 contains one atom of carbon and two atoms of oxygen, and that oxygen originally came from the water you electrolyzed to make breathable air. So if you're venting CO2 overboard, you're essentially throwing away oxygen, which means you need to electrolyze more water to replace it, which means you need to launch more water from Earth. And launching water to orbit costs roughly $10,000 a kilogram at minimum. So NASA engineers developed a system called the Sabatier reactor, which takes that carbon dioxide and reacts it with the hydrogen left over from electrolysis. Remember, the hydrogen that the early systems just vented into space, and combines them in the presence of a catalyst to produce methane and water. The water goes back into the system to be electrolyzed again for oxygen, and the methane gets vented overboard. This closes the loop partially. You're still losing the hydrogen that's locked up in the methane, so the loop isn't perfectly closed, but it dramatically reduces the amount of water you need to launch from Earth. The Sabatier system was installed on the station in 2010, and it was a significant upgrade to the life support architecture. There's been ongoing research into even more advanced systems that could crack that methane to recover the hydrogen, which would close the loop even further, but that technology hasn't been deployed on the ISS yet. And then there's water recycling, which is honestly one of the most impressive systems on the station, and also the one that gets the most jokes. The water recovery system, located in the Tranquility Node module, takes in basically every source of wastewater on the station. Humidity condensate from the air, which is the moisture from crew breath and sweat that gets collected by the cabin air conditioning system, and yes, urine, and processes it back into potable drinking water. The urine processing assembly uses a distillation process. But here's the challenge. Distillation on Earth relies on gravity. You heat the liquid, the vapor rises, you collect it, you cool it, and you have purified water. In microgravity, there's no rising. The vapor doesn't separate from the liquid in any predictable way. So the system uses a rotating distillation drum that creates artificial gravity through centrifugal force, spinning the urine to separate the vapor from the brine. The vapor is then fed into the water processing assembly, where it joins the humidity condensate and goes through a series of filtration beds, catalytic oxidation reactors that break down organic contaminants, and ion exchange beds that remove dissolved minerals and salts. The final product is tested by onboard sensors, and the water that comes out is actually cleaner than most municipal tap water on Earth. Astronauts sometimes say it's the best water they've ever tasted, which is either a testament to the engineering or a sign that they've made peace with the source material. The overall water recovery rate is somewhere around 90%, meaning that for every 100 kilograms of wastewater that goes in, about 90 kilograms of clean water comes out. The remaining 10% is concentrated brine that's too difficult to process further with current technology and gets stored as waste. NASA has been working on brine processing systems that could push that recovery rate even higher, toward 98%, because every percentage point matters when you're talking about future missions to Mars, where resupply from Earth won't be an option. And there's one more piece of the atmospheric puzzle that doesn't get talked about much, but is absolutely essential: trace contaminant control. Even with oxygen flowing and CO2 being scrubbed, the cabin air accumulates all sorts of low-level pollutants, off-gassing from equipment, from plastics, from adhesives, from paint, metabolic byproducts from the crew, cleaning products, science experiments. The trace contaminant control system uses activated charcoal beds to absorb a wide range of organic compounds, plus a catalytic oxidizer that heats contaminated air to break down certain chemicals into carbon dioxide and water, which then get handled by the other systems. It also includes specific filters for things like ammonia. Without this system, the station's atmosphere would slowly accumulate a cocktail of low-level toxins that over months and years could cause serious health problems. So when you put it all together, electrolysis for oxygen, zeolite beds for CO2 removal, the Sabatier reactor to recover some of that lost oxygen, water recycling from humidity and urine, trace contaminant control, you have an environmental control and life support system, ECLSS, that is essentially a miniature version of Earth's biosphere, engineered into racks of machinery that fit inside a room. It's not a perfect closed loop. You still need resupply of water and nitrogen and various consumables. But it's far more closed than anything that came before it, and every improvement moves the technology closer to what you'd need for a truly self-sustaining habitat far from Earth. And what's remarkable is how much of this technology was developed iteratively, through actual operational experience on the station. Systems were designed on the ground, launched, installed, and then refined based on how they actually performed in microgravity with real crews over real time. The urine processing assembly, for example, went through significant troubleshooting in its first years of operation. Calcium sulfate from the urine kept clogging the distillation drum, and engineers had to develop new pretreatment chemicals to prevent the buildup. The CDRA zeolite beds degraded faster than expected and needed replacement. The Sabatier reactor had to be tuned and adjusted. This is the reality of engineering at this level of complexity. You design the best system you can, you fly it, and then you learn from what actually happens. Which brings us to something that doesn't always get the attention it deserves: how the station is actually assembled and maintained in orbit. because the tools and techniques developed for building and repairing the ISS represent their own category of engineering achievement. And at the center of that story is something the Canadians contributed that turned out to be one of the most indispensable pieces of hardware on the entire station. A robotic arm called Canadarm2, officially the Space Station Remote Manipulator System, and its even more remarkable companion, a smaller two-armed robot called Dextra, the special-purpose dexterous manipulator. And Dextra is something else entirely, so let's take our time with both of them. Canadarm2 grew out of the legacy of the original Canadarm, which flew on the space shuttle starting in 1981. That first arm was a huge deal. It was Canada's signature contribution to the shuttle program, and it worked beautifully for deploying and retrieving satellites, supporting spacewalks, and inspecting the orbiter's heat shield. But it had limitations. It was bolted to the shuttle's payload bay. It could reach about 15 meters, and it had one end fixed in place, so its workspace was constrained to whatever it could swing toward from that single shoulder joint. Canadarm2 threw all of those constraints away. It launched to the station in April 2001 on STS-100, and when the crew got it assembled and powered up, what they had was a 17-meter-long robotic arm with 7 motorized joints. Think of it like a human arm with a shoulder, an elbow, and a wrist, except each of those joints can rotate in ways your arm can't. The whole thing masses about 1,700 kilograms. But here's what makes it fundamentally different from its predecessor. It has no fixed base. Each end of the arm is identical. There's a latching end effector at both tips, and either one can grab onto a power and data grapple fixture mounted on the station's exterior. So the arm can literally walk itself across the outside of the station, end over end, like an inchworm. It grabs on with one end, releases the other, swings around, grabs a new fixture further along, releases the first end, and repeats. This means it can reposition itself to reach almost any part of the station's exterior, which is critical when you're assembling and maintaining a structure that stretches longer than a football field. The arm is operated from inside the station, primarily from the cupola workstation in the Destiny Laboratory module, or from the Robotics workstation in the cupola itself. Actually, let me be more precise. The main robotics workstations are in the Destiny Lab and in the cupola, that gorgeous 7-windowed observation dome that was installed in 2010 on the nadir port of the Tranquility node. The cupola gives operators a direct view of whatever the arm is doing, which matters enormously when you're maneuvering a multi-ton module or catching a free-flying cargo vehicle. The arm can also be operated from the ground, from mission control, for routine repositioning tasks that don't need a human watching out the window. And the tasks this arm performs are extraordinary. It birthed nearly every major module added to the station after its installation. When a Japanese H-2 transfer vehicle or a SpaceX Dragon capsule arrives at the station, it doesn't dock autonomously the way a Soyuz or Progress does. Instead, it flies to a point about 10 meters below the station and holds position there, and then Canadarm2 reaches out, grapples a fixture on the vehicle, and gently swings it into place on one of the berthing ports. This is called the capture and berth approach, and it was chosen for these vehicles partly because berthing ports can be larger than docking ports, which means you can transfer bigger cargo through them. The arm makes this possible. Without it, you simply couldn't get those vehicles attached. But the arm's most remarkable partner is Dextra, and this is where the robotics story gets genuinely fascinating. Dextra arrived at the station in March 2008 on STS-123. It's a torso-shaped robot with 2 arms, each about 3.5 meters long, and each arm ends in what's essentially a robotic hand, a set of motorized tools that can grip, rotate, and manipulate objects with surprising precision. Dextry rides on the end of Canadarm2 like a hand on a wrist. So you have this big arm that can walk across the station and position itself anywhere. And then at the tip of that arm, you have this smaller, more dexterous robot that can do fine manipulation work. The combination gives you reach and precision simultaneously. Here's why this matters so much. Spacewalks, extravehicular activities, EVAs, are incredibly expensive in every sense of the word. Each one requires hours of preparation, including pre-breathing pure oxygen to purge nitrogen from the astronaut's blood and prevent decompression sickness. The spacesuits themselves are complex life support systems that need extensive checkout. There's always risk. You're putting a human being outside a spacecraft in the vacuum of space, and things can go wrong. In July 2013, the Italian astronaut Luca Parmitano had his helmet begin filling with water during a spacewalk due to a blockage in his suit's cooling system. Water in microgravity doesn't drain. It forms a growing blob that migrated across his face, covering his eyes, nose, and eventually threatening his ability to breathe. He had to navigate back to the airlock, essentially blind, by memory and feel. He made it, but it was one of the most harrowing moments in ISS history. Every EVA you can avoid by using robots instead is a reduction in risk to human life. And Dextray has proven remarkably capable at replacing tasks that previously required spacewalks. It can swap out external equipment, things like orbital replacement units, which are standardized boxes containing cameras, computers, pumps, and other components that were specifically designed to be robotically serviceable. The station's designers had the foresight to create these modular units with standard grapple interfaces and bolt patterns that Dexter's tools can engage. So when a camera fails or a pump wears out, ground controllers can schedule a robotic operation, often conducted overnight while the crew sleeps, where Dexter removes the failed unit, stows it, retrieves a spare from an external storage platform, and installs it. The crew wakes up and the repair is done. Think about what that represents from an engineering philosophy standpoint. The station was designed, at least in part, with the understanding that things would break, that components would need regular replacement, and that the replacement process itself needed to be engineered as carefully as the components. This is a concept called design for serviceability, and the ISS pushed it further than any previous spacecraft. Those orbital replacement units are like cartridges, standardized, swappable, robotically accessible. It's the same thinking that leads you to design a car engine so the oil filter is easy to reach rather than buried behind the transmission. Except here, the mechanic is a robot working in vacuum, in temperature extremes ranging from about -150 degrees Celsius in shadow to +150 in direct sunlight, and the car is traveling at 7.7 kilometers per second. Now, even with Canadarm2 and Dexter handling more and more tasks, spacewalks remain essential for work that requires human judgment, improvisation, and the kind of complex manipulation that robots still can't match. Over the life of the ISS, more than 260 spacewalks have been conducted for assembly and maintenance, totaling well over 1,600 hours of cumulative EVA time. That's an astonishing number. The station has essentially been a construction site in orbit for over 2 decades, and some of those spacewalks have involved genuinely heroic improvisational repair work. One of the most dramatic sequences happened in late 2007 and early 2008, when the crew discovered that the solar alpha rotary joint on the starboard truss, that's the massive bearing that allows the solar arrays on one side of the station to rotate and track the sun, was vibrating and drawing excessive current. When astronauts went outside to inspect it, they found metal shavings contaminating the bearing race. The bearing ring, which was about 3 meters in diameter, had a damaged surface that was grinding against the trunnion bearings. Over a series of spacewalks, astronauts cleaned out the metal debris, lubricated the bearing surfaces, and eventually replaced the bearing components. This was intricate mechanical work, done in bulky pressurized gloves, on hardware that was never really designed to be repaired this way. They figured it out as they went. Ground teams designed new procedures, tested them in the neutral buoyancy laboratory, that enormous swimming pool at Johnson Space Center where astronauts practice EVAs on submerged mock-ups, and uplinked the instructions to the crew. This pattern of diagnosing problems, devising solutions, testing them on the ground, and executing them in orbit is one of the defining characteristics of ISS operations. The station is, in a very real sense, an ongoing engineering experiment in long-duration maintenance of complex systems. Every failure becomes a lesson. Every repair becomes a procedure that future missions can build on. And speaking of the solar arrays that rotary joint supports, let's talk about power, because keeping the ISS electrically alive is its own fascinating engineering story. The station's primary power source is sunlight, captured by 8 enormous solar array wings mounted on the integrated truss structure. Each wing consists of 2 blankets of photovoltaic cells that unfold like an accordion, and when fully deployed, each wing stretches about 34 meters long and 12 meters wide. Together, the 8 wings provide roughly 240 kilowatts of electrical power when they're in direct sunlight, enough to power about 40 average American homes. But of course, the station spends roughly 35 minutes of every 92-minute orbit in Earth's shadow, so you need batteries to store energy for the dark periods. The original batteries were nickel-hydrogen cells, a technology chosen for its reliability and tolerance for the charge-discharge cycling that orbital mechanics demands, roughly 16 cycles every single day, thousands upon thousands of cycles over the station's lifetime. But nickel-hydrogen batteries are heavy and bulky, and by the mid-2000s, they were aging. So between 2017 and 2021, the station underwent a major battery replacement campaign, swapping out 48 nickel-hydrogen batteries for 24 lithium-ion batteries. Each lithium-ion battery has roughly the same energy storage capacity as 2 of the old nickel-hydrogen units, so you need half as many, which saves mass and frees up space on the truss. This swap was accomplished through a combination of spacewalks and robotic operations, Dextray and Canadarm. 2 did much of the heavy lifting, literally moving adapter plates and battery units into position, while astronauts made the final electrical connections. The power system doesn't end at the arrays and batteries, though. The electricity generated by the solar cells is direct current at about 160 volts. It passes through sequential shunt units that regulate the voltage, then into battery charge-discharge units that manage the flow to and from the batteries, and then through DC to DC converter units that step the voltage down to the 124 volts used by the American segment's equipment. The Russian segment, interestingly, operates on a different voltage standard, 28 volts DC, a legacy of Russian spacecraft design conventions, so there are converter units at the interface between the 2 segments. Power is shared between them through those converters, which was one of many technical integration challenges that had to be solved when you merged 2 fundamentally different engineering traditions into one station. And that challenge of integration, of making systems designed by different countries, in different languages, using different engineering standards, actually work together seamlessly is honestly one of the most underappreciated aspects of the entire ISS program. It shows up everywhere, not just in power systems. The docking mechanisms, for instance. The station uses two different types of docking and berthing interfaces, and making sure a vehicle built in Japan can berth at a node built in Italy and pressurized by a system designed in Alabama requires an extraordinary level of coordination. There are thousands of interface control documents that specify exactly how every connection works: mechanical, electrical, data, fluid, the bolts, the seals, the connector pin assignments, the software protocols, all of it negotiated and agreed upon between international partners who sometimes had very different ideas about how things should be done. This brings us to something that operates quietly in the background, but is absolutely essential to everything happening on the station: the command and data handling system. The network of computers that ties the whole sprawling complex together and keeps it functioning as a coherent whole. And the architecture of that system reveals something really fascinating about how engineers solve the problem of trust in complex systems. Because here's the thing: you can't just have one computer running the International Space Station. That would be insane. If that single computer failed, you'd lose control of everything. Attitude control, thermal regulation, power distribution, life support commands, all of it gone. So instead, the station uses a distributed, redundant, tiered architecture, and the way it's layered is genuinely elegant. At the top level, you have what are called the command and control multiplexer demultiplexer computers, the C and CMDMs. These are the brains of the American segment's operations. They're arranged in a redundant set. There's a primary, a backup, and sometimes a standby. And they handle the highest level decision-making. They coordinate commands coming up from mission control in Houston. They manage the overall mode of the station. And they pass instructions down to lower-tier computers that control specific systems. Below them, you have local area network MDMs, and then, at the lowest tier, you have MDMs dedicated to individual systems: power, thermal control, guidance, and navigation, the works. Each of these tiers can talk to the ones above and below it through a network, and the whole thing is designed so that if one box fails, another can pick up the load. Now, the Russian segment has its own computer system, naturally. Their central computers handle attitude control and navigation for their modules, and they interface with the American system through, you guessed it, more carefully negotiated data protocols. The two systems share critical information, especially about the station's orientation in space and its orbital parameters, but they're fundamentally separate architectures that have learned to talk to each other. Think of it like two different operating systems sharing files over a network. It works, but it took a lot of engineering to make it work. And here's what's wild. The computers on the station, at least the original ones, are not powerful by any modern standard. We're talking processors that would be laughably slow compared to the phone you probably have on your nightstand right now. But they don't need to be fast in the way your phone is fast. They need to be reliable. They need to keep running without crashing in an environment where cosmic radiation can flip a bit in memory at any moment. That's a real thing, by the way. A high-energy particle zips through a computer chip and changes a 0 to a 1 or vice versa. It's called a single-event upset, and in space, it happens far more often than you'd think because you're above most of Earth's protective atmosphere and magnetic shielding. So the station's computers use radiation-hardened components, error-correcting memory, and software that constantly checks itself. The redundancy isn't just in having backup boxes, It's baked into the logic of the software itself. The software, incidentally, is another one of those quiet marvels. Millions of lines of code, written by teams across multiple countries, all of it having to work together in real time. The American segment's flight software has gone through countless updates over the years, uploaded from the ground, tested, verified, and activated, sometimes while the crew is asleep, sometimes during a quiet period in operations. Every update is a careful, methodical process because the consequences of a software bug up there are not abstract. A bad line of code could misfire a thruster, or fail to command a cooling pump, or misinterpret a sensor reading in a way that triggers a false alarm, or worse, fails to trigger a real one. And that brings up something worth sitting with for a moment. The ISS has been continuously inhabited since November of 2000. That's over 2 decades of people living and working in space without interruption. And in all that time, the station has never had a catastrophic failure. There have been close calls. We talked about the Mir fire, the Mir collision, the Parmitano helmet incident, and the ISS has had its share of scares too. Ammonia leaks in the cooling system. A brief loss of attitude control when a newly arrived Russian module unexpectedly fired its thrusters in 2021. That was the Nauka module, and for about 47 minutes, the station was slowly rotating in a way nobody planned, which is a genuinely alarming situation when you think about the stresses on those long truss segments and solar arrays. But the crew and the ground teams worked the problem, regained control, and the station came through it. Every time something has gone wrong, the combination of redundant systems, well-trained crews, and deeply experienced ground controllers has caught the problem before it became a disaster. That track record isn't luck. It's the result of a design philosophy and an operational culture that treats every anomaly as something to be understood, documented, and learned from. There's a phrase you hear in spaceflight operations: failure is not an option. And it's become a bit of a cliché, but the reality behind it is more nuanced and more interesting than the slogan suggests. Failure absolutely happens. Components break, software glitches, humans make mistakes. The real philosophy is that failure must be anticipated, contained, and recoverable. Every critical system has a backup. Every backup has a workaround. And every workaround has been practiced in simulations on the ground over and over, so that when the moment comes, the response is almost automatic. The crew training for ISS expeditions takes about 2.5 years, and it happens across multiple countries. An astronaut assigned to a long-duration mission will train in Houston for American segment systems, in Star City outside Moscow for Russian segment systems and Soyuz operations, in Tsukuba, Japan for the Japanese Kibo module, in Cologne, Germany for European Columbus module operations, and in Montreal for the robotic arm. They learn to operate every major system, to respond to emergencies: fire, depressurization, ammonia leak, the big three, and they practice working together as a crew, even though they may come from completely different spaceflight traditions. A NASA astronaut, and a Roscosmos cosmonaut, and a JAXA astronaut, and an ESA astronaut, all learning each other's systems, each other's languages. Russian and English are the 2 working languages on the station, and each other's ways of solving problems. And then they go up there, and they live together in a space about the size of a 6-bedroom house, though most of that volume is packed with equipment, so the actual livable space feels more like a modest apartment. They sleep in crew quarters that are roughly the size of a phone booth. Small padded compartments where they zip themselves into a sleeping bag that's attached to the wall so they don't drift around They eat rehydrated and thermostabilized food, though the variety has gotten much better over the years. Fresh fruit arrives occasionally on cargo vehicles, and it's always a morale boost. Imagine craving an apple for weeks and then finally getting one. They exercise for about 2 hours every day, which sounds like a lot until you understand why. In microgravity, your body starts to change almost immediately. Without the constant load of gravity, your bones lose calcium, your muscles atrophy, your cardiovascular system deconditions because your heart doesn't have to work as hard to pump blood upward. Early space station crews on Salyut and even early Mir missions came back to Earth in rough shape. Some could barely walk. The exercise protocols on the ISS, developed through hard experience over decades, are specifically designed to counteract those effects. There's a treadmill. Actually, there are two. A stationary bicycle and a resistive exercise device called ARED, the Advanced Resistive Exercise Device, which uses vacuum cylinders to simulate the feeling of lifting weights. Crew members who stick to the exercise regimen religiously come back in remarkably good condition compared to earlier eras of spaceflight. Not perfect, but functional. They can walk off the Soyuz capsule, sometimes a little wobbly, but they can do it. The science that happens on the station is the whole reason it exists, or at least the reason that gets cited most often. And it's genuinely wide-ranging. Materials science experiments that take advantage of microgravity to study how crystals grow without the distorting influence of convection currents. Protein crystallography that has produced better crystal structures of biological molecules, which helps drug designers on Earth understand how to target diseases. Combustion research. Fire behaves very differently without gravity, forming strange spherical flames instead of the teardrop shape you're used to, and studying that teaches us fundamental things about combustion chemistry that are hard to isolate on Earth. Earth observation, obviously. The station's orbit carries it over most of the populated world, and the crew and the station's instruments provide a unique vantage point for studying weather patterns, agricultural changes, urban growth, and natural disasters. There's also a tremendous amount of research into human physiology itself. The station is essentially a long-duration experiment in what happens to the human body when you remove gravity, and every crew member is both operator and test subject. But here's the thing that often gets overlooked when people talk about ISS science. Some of the most valuable outcomes aren't individual experiments. They're the operational knowledge, the engineering knowledge of how to keep humans alive and working in space for months at a time, how to maintain a spacecraft that can't come in for service, how to manage an international team across language barriers and cultural differences and time zones, how to handle emergencies 350 kilometers above the nearest hospital. That knowledge doesn't show up in a single published paper. It lives in procedures manuals, in training curricula, in the institutional memory of thousands of engineers and flight controllers and astronauts. And it's the knowledge that will make the next step possible. Because the ISS won't last forever. Its structural life has been extended multiple times. Originally designed for a 15-year operational period, it's now been approved through at least 2030, and there are discussions about extending to 2028 or even beyond, though the structural fatigue of those modules, some of which have been in orbit since the late 1990s, is a real and growing concern. Micrometeorite impacts accumulate. Thermal cycling. The station goes from blazing sunlight to deep shadow every 90 minutes, expanding and contracting with each cycle, gradually fatigues metal joints and seals. The Russian segment in particular has shown signs of aging, with occasional air leak issues that crews have had to track down and patch. So the question of what comes after the ISS is not hypothetical. It's actively being planned right now, and the answer is shaping up to be something quite different from what came before. A transition from a single massive government-operated station to a model where commercial companies build and operate their own stations in low Earth orbit, with NASA and other agencies as customers rather than operators. That's a huge shift in thinking. For decades, if you wanted to do research in microgravity, there was essentially one address in low Earth orbit, the ISS. Governments built it. Governments maintained it. Governments decided who got to use it and when. But the model that's emerging now flips that relationship. NASA's Commercial Low Earth Orbit Destinations Program, often shortened to CLD, is essentially saying to private industry, "We'll help fund development. We'll commit to buying services once you're operational. But you design it, you build it, you own it, and you can sell time and space to whoever else wants it. Other governments, pharmaceutical companies, materials science firms, media companies, tourists, whoever." NASA becomes a tenant, not a landlord. And if you think about it, this follows a pattern that's already been proven. Remember how the ISS relied on the space shuttle for assembly and crew rotation for years? When the shuttle retired in 2011, NASA turned to commercial providers for cargo first. SpaceX with Dragon, Orbital Sciences with Cygnus, and then for crew, with SpaceX's Crew Dragon and Boeing's Starliner. That progression from government-only to commercial partnership worked. Not perfectly, and not without delays, but it worked. The Commercial Crew Program got astronauts to the ISS at a fraction of what the shuttle cost per seat, and it did it while allowing those companies to sell seats to other customers too. So extending that logic to the station itself isn't as radical as it might sound. It's the next step on a path that's already been walked partway. As of the early 2020s, NASA awarded funding to several companies working on commercial station concepts. Axiom Space is probably the furthest along in one sense. They've already attached their first module, Axiom's Habitat module, to the ISS itself, with plans to add more modules and eventually detach the whole Axiom segment to become a free-flying station when the ISS is deorbited. That's a clever approach, right? You bootstrap your new station by literally bolting it onto the old one, using ISS infrastructure while you build out your own capability. Then when the ISS goes away, you're already up there, already tested, already operational. Jeff Bezos's Blue Origin is working with Sierra Space on a concept called Orbital Reef, envisioned as a mixed-use business park in space. Their words, not mine, though it does capture something about the commercial intent. Vast Space, a newer company, has been developing a single launch station concept called Haven, designed to go up on a single heavy-lift rocket and provide immediate habitable volume. Each of these approaches reflects lessons learned from the ISS, sometimes by emulation and sometimes by deliberate contrast. The ISS taught us that assembling a station from dozens of launches over a decade is extraordinarily expensive and complex. So several of these commercial concepts are designed to launch in far fewer pieces, taking advantage of larger payload fairings on rockets, like SpaceX's Starship or Blue Origin's New Glenn. The ISS taught us that international partnerships add resilience, but also add coordination overhead. Those negotiated interface protocols between Russian and American segments, the 5 partner agencies with different engineering standards and different political pressures. Commercial stations will likely have simpler governance structures, at least initially, though international customers will still bring some of that complexity. But here's what's really interesting about this transition. It's not just about building a replacement for the ISS. It's about whether the economics of low Earth orbit can actually work as a commercial enterprise. The ISS costs NASA roughly $3 to $4 billion a year to operate. That's a lot of money, but it's government money spent for government purposes: science, technology development, international diplomacy, national prestige. A commercial station has to either cost dramatically less to operate or generate enough revenue from diverse customers to cover its costs and turn a profit. And the honest truth is, nobody's entirely sure yet whether that math works. The market for microgravity research is real, but still small. Space tourism is real, but still expensive. Manufacturing in space, things like fiber optic cables or semiconductor crystals that might be higher quality when made in microgravity, is promising, but mostly unproven at commercial scale. So there's genuine uncertainty here, and that's worth sitting with for a moment. The ISS was built during an era when governments were willing to spend enormous sums on space infrastructure for strategic and scientific reasons. The commercial era assumes that private capital and market demand can sustain something similar. Maybe it can. The history of aviation followed a somewhat parallel path. Governments funded the early development, military needs drove the technology, and eventually commercial aviation became one of the largest industries on Earth. But that transition took decades and wasn't guaranteed. There were plenty of bankrupt airlines along the way. Now, regardless of how the commercial station story plays out, there's one more piece of the ISS legacy we should talk about, and it's the one that might matter most in the long run. The ISS has been, above all else, a rehearsal for going further. Everything NASA and its partners have learned about keeping humans alive in space for 6 months, for a year, Scott Kelly's year-long mission in 2015 and 2016, or the even longer stays by Russian cosmonauts, all of that is directly applicable to missions to the Moon and Mars. The life support systems we talked about earlier, the water recycling and oxygen generation and carbon dioxide scrubbing, those are the ancestors of the systems that will have to work on a spacecraft traveling to Mars for 7 months with no possibility of resupply. The exercise protocols, the bone density monitoring, the radiation exposure tracking, all of it feeds forward. And think about what the ISS has taught us about the psychology of long-duration spaceflight. This is something that doesn't always get the attention it deserves, but it's critical. When you put a small group of people in a confined space for months at a time, with no ability to leave, with communication delays to family back home, with the stress of operating complex and sometimes malfunctioning equipment, the interpersonal dynamics matter enormously. The ISS has been a laboratory for understanding crew cohesion, for developing scheduling practices that balance productivity with downtime, for learning how much autonomy crews need versus how much ground control should direct. Early in the ISS program, schedules were packed so tightly that crews felt micromanaged and morale suffered. Over time, mission planners learned to build in more discretionary time, to give crews ownership over some of their scheduling, to prioritize communication with families. These are soft lessons, hard to quantify, but they'll be essential for a Mars mission where the crew will be so far from Earth that real-time conversation is impossible. The communication delay can be over 20 minutes each way. The medical knowledge is another enormous legacy. We now have detailed longitudinal data on what happens to the human body in microgravity over periods of months to a year. We know about the fluid shift toward the head that can affect vision. Some astronauts have come back with measurably changed eyesight due to increased intracranial pressure, a condition called spaceflight-associated neuroocular syndrome. We know about the immune system changes, the altered gut microbiome, the kidney stone risks from calcium lost by bones. None of these problems have been fully solved, but they're understood now in ways they simply weren't before the ISS provided a platform for studying them systematically over 20+ years of continuous habitation. And there's something poetic about that, if you think about it. This enormous, ungainly, magnificent structure, 420,000 kilograms of metal and wire and solar panel, the size of a football field, assembled by the hands of astronauts from 15 nations over more than a decade. It was never really the destination. It was always the classroom, the rehearsal space, the proving ground. Every system that worked, every system that failed, every emergency that was contained, every repair that was improvised, every lesson about how humans and machines interact in the most unforgiving environment we've ever tried to inhabit. All of it is preparation for what comes next. When the ISS eventually reaches the end of its operational life, the current plan is for a controlled deorbit. NASA has contracted SpaceX to build a specialized deorbit vehicle, essentially a very large and powerful spacecraft whose job is to push the station into a precise trajectory that brings it down over an uninhabited stretch of the South Pacific, an area sometimes called the spacecraft cemetery because it's where other large objects like Mir have been intentionally brought down. The station is too large to burn up completely on re-entry. Significant chunks of dense metal, parts of the truss, the docking adapters, some of the heavier equipment, will survive the heat of re-entry and splash into the ocean. It's a controlled process, carefully calculated, but there's something undeniably bittersweet about it. This thing that took so much ingenuity and cooperation and sheer stubbornness to build, deliberately guided into the atmosphere to break apart and sink. But that's how engineering works, isn't it? Nothing lasts forever. Bridges are eventually replaced. Power plants are decommissioned. The most advanced aircraft of one generation becomes the museum piece of the next. What endures is the knowledge, the understanding, the accumulated wisdom of what works, what doesn't, and why. And right now, as you're lying there, the ISS is overhead. Maybe not directly overhead at this exact moment, but it's up there, circling the Earth every 90 minutes or so, moving at about 28,000 kilometers per hour, crewed by 6 or 7 people who are right now either sleeping in their little phone booth-sized quarters, or running an experiment, or exercising on a treadmill strapped in with bungee cords, or eating a pouch of rehydrated food while floating next to a window that shows them the entire curve of the planet below. The lights of cities sliding past beneath them. The thin blue line of the atmosphere, impossibly delicate when you see it from that altitude. The sun rising and setting 16 times in their day. It's been up there, continuously inhabited, since November of 2000. More than 2 decades of unbroken human presence in space. Babies born on the day the first crew arrived have graduated from college. And through all of that time, through all the technical crises and political tensions and budget fights and close calls, the lights have stayed on. The air has kept flowing. The water has kept cycling. People have kept living and working 350 kilometers above the Earth, inside a machine that is, when you really look at it, one of the most extraordinary things our species has ever built. Not because it's the biggest or the most powerful or the most elegant, but because it works. Because thousands of engineers and scientists and astronauts and flight controllers from countries that don't always agree on much of anything figured out how to make it work, together, for longer than anyone originally planned. Because every bolt and every weld and every line of software and every procedure and every manual represents someone solving a problem so that people could live where people were never meant to live. And that's enough to think about as you drift off. That right now, tonight, there are people up there, floating in the dark, circling the world, keeping the station running, carrying forward everything we've learned. The hum of fans and pumps around them, the soft glow of instrument panels, the whole improbable, magnificent contraption holding steady in the void. It's up there, and it works. And someday, because of everything it taught us, we'll go further. But for now, that's plenty. That's more than enough. Let that thought settle, and let everything else go quiet.